Okay, in our last video, we saw the concept of Kw, and we said that Kw is equal to the concentration of the hydronium ion, which is H3O+, multiplied by the concentration of the hydroxide ion. And we said that Kw is always going to be equal to 1.0 times 10 to the negative 14th moles per liter squared, right? All right, but the interesting thing with this is the range, the potential range for the hydronium ion, meaning this ion right here. Okay, so the range can vary wildly. So the concentration of H3O+, that hydronium ion, whoops, let me clean this up, in aqueous solutions can vary from 10 molar all the way to 10 to the negative 14th molar, meaning there's 14 orders of magnitude. That's huge, right? So chemists, when they deal with these giant orders of magnitude from incredibly large to incredibly tiny numbers, oftentimes switch to things like log scales. So that's what we do here. So let's just make a note. With a range this big, it is more convenient to use a log scale. All right, so log scales are kind of unique, and if you haven't used them before, basically an increase in 1 on a log scale is the same as an increase of 10, right? So if you go up 2 in a log scale, that's the equivalent of 10 times 10, or 100, or 3 would be 10 times 10 times 10. So it's just a lot easier when you're dealing with 14 orders of magnitude to work in the scale. So let me show you how we do this as chemists. We use the pH system. And what P stands for in a mathematical sense, this P is mathematical code for negative log. They're the exact same thing. Okay, so P is just math term for negative log, and then we take negative log of the concentration of H+. It's kind of irritating that they still use this H+, but really you can treat this the same as H3O+. Like we saw, the problem with the Arrhenius theory is H+ doesn't exist as a free ion in solution. We know in reality it's going to immediately get bonded to a water molecule, and we'd be talking about H3O+. But same idea. All right, so we've got this cool system set up where we can kind of narrow down this range into a more reasonable group. And we said that P is the same as negative log, right? All right, so if you're familiar with working with logs, we can actually do the reverse, right? So let's say we want to calculate H+ concentration, but we're given a pH. Well, in order to do that, we've got to use some of our log rules. I'm not going to go into that in much detail. You'll probably cover it in your math classes. But you can do this calculation where you do 10 to the negative pH will tell you the concentration of your hydronium ion. And like I said, this is always the same as H3O+. All right. So let's do a few sample calculations and try working with these new math formulas that we have, okay? So I'll just do a few situations from the book. So find the pH if the concentration of H+ is equal to 1.0 times 10 to the negative 5th molar, right? So molar, if you remember, is the same thing as moles per liter. That's just what it stands for. Okay, so in order to do this, we know that pH is equal to negative log of H plus concentration. So we could type this into our calculator as negative log times 1.0 times 10 to the negative fifth. And we would get an answer out that is equal to 5.0, right? So not too bad. pH of 5.0, as we'll see, is slightly acidic. Okay, but let's do something a little bit different now. And this is always something that throws students for a loop. Let's find the pH if the hydroxide concentration is equal to 1.0 times 10 to the negative ninth molar. All right, so this one's going to be a little bit different. The problem is we're not given the concentration of H plus directly, right? So let's just make a note. So we aren't given H plus, all right? But can we find it? Absolutely, right? If you remember, Kw is equal to the hydroxide concentration times our hydronium concentration. So let's rearrange this and try to solve it for H3O plus, right? That just means that H3O plus would be equal to Kw over our concentration of OH minus, all right? We know that Kw is a constant. It's just going to be 1.0 times 10 to the negative 14th molar. And we were given the concentration of hydroxide here. So I just plugged this in down below. I'd say 1.0 times 10 to the negative ninth molar. Our molarity is essentially, oops, sorry, this should be molarity squared, excuse me, and we'd be left with the units of molar left over. So if we go ahead and we do this, we're going to be left with a concentration of 1.0 times 10 to the negative fifth molar, right? And like I said, this is the same as H plus concentration. All right, so now we're set up to do the problem. So we could say, well, pH is equal to negative log of our H plus, which we just found. So we could type it into our calculator as negative log of 1.0 times 10 to the negative fifth, which in this case comes out to be 5.0. So there's a lot of tricks you can do. In particular, using this equation, you can kind of convert back and forth, where if you're given your concentration of hydroxide, you can find your concentration of your hydronium ion. There's other examples in the book as well that do kind of this reverse example where we can find the concentration if we're given the pH. So you might want to spend a little bit of time going through some of those book problems, trying to work them out on your own. All right, let's take a look at the pH range. All right, so the pH range goes from 0 all the way to 14. So you can imagine if we split this smack down the middle, that would be at 7, right? Halfway in between each side. Well, if we're in the middle, this is a situation where things are neutral. That means we've got an equal amount of hydroxide and hydronium ions in solution. So this is where OH minus equals H3O plus. In fact, let's just get rid of the parentheses there. All right, and then on this side, from 7 to 14, this is going to be basic. And if you remember, basic means we've got more hydroxide than we do hydronium. All right, and then over on the other side, as you can probably guess, this is going to be acidic. And that's going to be the opposite. It's going to be where we have more hydronium than hydroxide. But obviously, this is a lot easier to wrap your head around. Is 0 to 14 are manageable numbers. When you're talking about 14 orders of magnitude, it's too many numbers. But it is important to remember that if you're comparing something that has a pH of 7 to something that has a pH of 8, right? We're not dealing with a small difference. And in fact, we'd be saying that something that's a pH of 8 has 10 times as much hydroxide as something that is pH 7. So we're dealing with orders of 10 for each difference that's 1 in the pH range. All right, I hope that makes sense. But if you have any questions, feel free to email me.